Okay, this is a worked example for the final exercise of exercises 5.8 in EGM90 Advanced Aerodynamics. So in this set of 4 exercises that all require you to think a little bit about the content that we've studied on molecular gas dynamics and rarefied gas flows, particularly for hypersonic applications. We did exercise 1 in the lectures, which was a case where you have a given velocity or molecular velocity distribution function and use that to compute fluid density and bulk velocity. Question 2 and question 3 I've asked you to have a go at yourselves, and I think you'll find they're pretty straightforward, but if you do have any problems with them, please come and see me. And what I'm going to do in this session is go through part 4, which was, this has come from part of actually a previous exam question. So the question states that given that this integral of the function x cubed, the exponential function to the minus ax squared dx, is given by 1 over 2a squared, that's just kind of a standard integral, which you often have to make use of when solving these problems where the distribution function contains that exponential function, which of course it often does because the Maxwellian form of that distribution function, the most common equilibrium form, has that exponential function as a part of it. So it just asks you to, given that, show that the mean molecular speed of an equilibrium gas is given by c bar, so 8 kBt, kB being the Boltzmann constant, over pi m, where m is the molecular mass to the power 1/2, so the square root of that function, and then basically work out what this is for oxygen molecules at a temperature of 273 K. Right, so let's give that a whirl. So this is 4, and it's going to require us to make use of the fact that the mean quantity, so the mean of a quantity Q, is given by the integral over all possible values of the molecular velocity. So across volume, so across velocity space, c, from minus infinity to plus infinity. So if this is a 3-dimensional problem, this is a 3-dimensional integral, and we looked at that in the class. But the question is interested in molecular speed, not molecular velocity. Now, c, we said, usually can be written in the components u, v, w. So the speed of a molecule is given by the square root of u squared plus v squared plus w squared. Now, one of the little tricks you have to do here, which I guess if you haven't seen an example like this, and we didn't look at this in the lecture, this is perhaps not obvious, is to think about, so we need to think about the distribution, the velocity, the speed distribution function rather than the velocity distribution function, which is what we've been thinking about so far. And often we see the speed distribution function of molecules written as GE of C. And this is the equilibrium speed distribution function, where C is no longer a vector, molecular velocity, it's molecular speed. Now you might be tempted to simply go, well, okay, so the form, let's just write down on the right hand side, I'm going to leave a gap, we're going to have to modify this in a moment. You know that the form of the velocity distribution function looks something like m over 2 pi Boltzmann constant t to the power 3 upon 2 times the exponential function, and this is what gives you that kind of Gaussian form for the distribution, minus m c squared 2 looks like this. And it's tempting to think, well, this c squared here is effectively like the speed of a molecule, But this was in the form where this was the velocity distribution function. And of course, for a given, if we've got a velocity space u, v, w, and we're interested in, and this is a probability function of finding a molecule at this point c bar with velocity c here. The probability of finding a molecule with a speed equivalent to that is obviously going to be greater than just the probability of finding it with this specific velocity, because there are multiple combinations of u, v and w that will give you this particular speed c. And in fact, any velocity vector that sits on the surface of a sphere of radius c bar, magnitude c, will have the same speed. So to convert a velocity distribution function into a speed distribution function, we take the same form, which is this here, we have to multiply it by the surface area of a sphere of radius c. And that takes into account the fact that, for example, a velocity vector in the opposite direction. Here, let's call it c dash. The magnitude of c dash, therefore the speed of c dash, vector c dash, is exactly the same as the magnitude of c. In fact, any velocity vector that we write that has the same length, has the same magnitude, and if you draw them all, you form the surfaces of a sphere, which is why to convert to a speed distribution function we need to add in this term here, to convert from a velocity distribution function, which we saw in the lectures, to a speed distribution function. And in the exam, that was one of the points that was missed by a lot of students. So the question asked for the mean speed of a molecule, not the mean velocity of the molecule. So we're looking for c bar, and we're just going to integrate over all possible speeds of the molecule. And of course, because we're talking about speeds, you can't get negative speeds. So we're interested in magnitude. It's going to be from 0 to infinity of, I think, sorry, I've just made a mistake. It should have been q times fe of c. So this form here. And this result is on the formula sheet for the exam. So the mean of a quantity q is q multiplied by the distribution function, integrated with respect to c over all possible values of c. So again, we're interested in the mean speeds. We just multiply, this time not the velocity distribution function, but the speed distribution function with respect to c. Okay, so all we have to do now is we've identified that the form of GE of C looks like this above. So we can just substitute into this expression here. So we can write C, mean value of C is going to be 4 pi C cubed n over 2 C. Now everything in this term here is constant. We think of a fixed gas, so a fixed molecular mass, fixed temperature, Boltzmann constant is constant, and obviously 4 pi is constant, so we can bring those outside the integral. And we're left with 2 pi. No, we can't do that just C yet, of course this 2 is inside here, so erase that. 4 pi m over 2 pi k dt 3.2 integration 0 infinity of c cubed dx to minus c squared 2 BC. And I guess at this point, given the question, which told us, if I quickly flip back to the question, that we could use this result that the integral from 0 to infinity of x cubed to exp to minus ax squared dx is that. Given that, we should be kind of looking out for a point in the problem where we've got an integral that's of that form, and we've arrived at that point now because we can rewrite this this integral here is of that form where a is kb t over n. That's right, isn't it? Yeah, that's correct. A, just double checking back to the form of that result. Yeah, that sounds about right. So if we let a be kbt over m, this thing becomes c cubed dxd of minus ax squared. And we've got the solution to that. The solution to this integral, according to that result, is that this thing works out as 1 over 2a squared when integrated through 0 and infinity. That's great news because we can just plug that result in now and we end up with 4 pi. I'll bring the 2 from that integration result out to the front here, and n over 2 pi kbt 4.2 times 1 over and over a squared all squared. And you can tidy that up a little bit further. C bar is equal to 2 pi and 2 pi kbt 4.2 n squared. And now basically, I'm going to cut a few steps here, but if you just work with the indices of these two terms here and combine the terms together, this boils down to 8 kbt n to the 5. So the tricky bit there really is that initial spot, or just remembering that if you're thinking about speed distribution, not velocity distribution, you have to do that little transformation back at this point up here. Add in this term to convert a velocity distribution function into a speed distribution function. The final part of the question then was to work out what the mean speed of oxygen molecules would be at 273 or 293 Kelvin. This can be CO2. This is simply going to be 8. The Boltzmann constant, which will be given to you in an exam situation, will be written on the front page of the exam paper. 1.381 times 10 to the minus 23 times 2 all over times molecular mass for oxygen. We worked this out in the lecture. It works out as 5.3 times 10 to the minus 26. And again, you wouldn't need to remember that. We wouldn't expect you to remember that value. That's the power half, of course. And if you work that out, that comes out to be 441 meters per second, which is a similar result. I think we did a problem similar to this in the lecture. I came out around about that value. And we pointed out in the lecture, of course, it's interesting that this is the mean speed of a molecule in oxygen, pure oxygen at 293 K. It's actually faster than the speed of sound. But of course, we're at a completely different scale here to the scale at which pressure waves travel. So we don't think about these molecules travelling around generating their own shock waves because they're travelling faster than the speed of sound. This is all happening at a completely different scale, which is interesting to note that the mean speed is actually pretty fast. So I hope that's useful, and that's the solution to question 4 in the final set of exercises on EGM90.